Okay, we've talked about the sampling distribution when we have an underlying population that's normal. But what happens if the population is not normal? So let's look at this uniform distribution here. So this distribution has a mean of 25 and a standard deviation of 14.4309. And you can see it's uniform because it's rectangular. And since it goes from 0 to 50 minutes, we should all remember that the height of this is 1 over 50. So now let's see what happens when we make a sampling distribution from that. And I did this using StatCrunch. Well, an applet in StatCrunch. So we took 1,000 samples, each of size 2, from that uniformly distributed population. So as you can see, when we graph the histogram, we get a mean of 25.2337 and a standard deviation of 9.8998. If you look at this distribution, it's starting to look approximately normal. So it's not quite because it goes up. It's got a couple peaks and it's got a dip between them. So it's, I would say, sort of normal. What about when we increase the sample size to 5 and we take 1,000 samples? Well, you see we have a mean of 24.8382. And we have a standard error of the mean of 6.4212. And if you look, this one looks even more normal than the last one. Okay, let's look at one more. So this time we have samples of size 50. And our mean is 24.9703. And the standard error is 2.0816. And this one looks very much normal. Very narrow, but still pretty normal. Okay, what if the population's skewed right? And skewed right and skewed left work out the same way in this. You just have to imagine the picture going the opposite direction. So here's our skewed right distribution. And you can see we have a mean of 17.207 and a standard deviation of 10.2855. Now, what if we take samples of 2? If we look at this histogram, we see that with sample sizes of 2, we're still a little bit skewed to the right. What happens if we increase our sample sizes to 5? Well, I think we're still skewed right just a little. And when we increase it to sample sizes of 50 and we take 1,000 samples, we're finally normally distributed, or at least approximately normally distributed. So regardless of what the underlying shape is, let's see, so it doesn't matter what the shape of the original distribution is. If the sample size gets large enough, then the sampling distribution of the mean is approximately normal. Now, this idea brings us to the central limit theorem. And the central limit theorem is one of the most important things in statistics, because this is how all of our inferential statistics that we'll cover in this class, not all of them, but at least all the ones in this class, this is how they work. So the central limit theorem says, regardless of the shape of the underlying population, the sampling distribution of X bar becomes approximately normal as the sample size n increases. And I cannot stress this enough. This is super important. That is the central limit theorem. So how large exactly does the sample size have to be before we can say that the sampling distribution is approximately normal? Well, that really depends on the shape of the underlying distribution. But we usually say if the distribution of the population is unknown, meaning they don't tell us what shape it has, or if it's non-normal, and non-normal just means it's not normally distributed, then we say the distribution of the sample mean is approximately normal if our sample size is greater than or equal to 30. So all this central limit theorem really means is that if we need to find the probability of a sample mean being within a certain range, we can treat it like it's a normally distributed curve and find the probability that way, as long as our sample size is large enough. So in the next video, we will pick up with some examples.